Good evening, thanks for coming. So the worlds of music and mathematics, to use my favorite term from Gareth Loy's text, Musimathics, are as diverse as the various subfields of mathematics or music taken alone. And one might question what use a composer has of theoretical ideas. So there has oftentimes been a split between composition and theory. The composers are the ones who do the creation, and the theorists are the ones who do the analysis. It's not the job of the analyst, or of the scientist, perhaps, in our interdisciplinary conversation to make sense of the world. I would actually argue the opposite perspective. I consider myself as a composer-theorist or a theorist-composer. And in other words, what I do in my creative work is I take a bunch of different compositional inputs, such as pre-compositional work, formal work, my theoretical training, perspectives from mathematics and psychoacoustics, and also some improvisation in order to create a compositional result. So I typically imagine myself kind of improvising on a real instrument when I start to compose, and I come up with this compositional results iteratively at the end of the process. And for me to kind of eliminate one universe, the analytical universe, or the compositional universe, and just to focus on the other, or to eliminate the analytical scrutiny to focus on creation, I think is to disservice my own artistic thinking. So tonight I'm going to focus the discussion on the fruition of a composition of mine that was performed in 2012. The piece is called Tinged, T-I-N-G-E-D, and is written for guitar and violin. And the mathematical process that this piece entails is the use of an alternative tuning system, which we can get into in a little bit. So my main proposition is that thinking about music and mathematics is in itself a compositional process, not only an analytical one. So one central concept that we can introduce is the concept of space. Usually when we think about musical space or sonic space, we think about the fusion of sound in space. So, for example, an engineer might figure out the intensity level of a sound pressure wave at a certain distance from a spherically radiating sound source. For example, perhaps a composer like Karlheinz Stockhausen would be interested in actually composing the movement of paths through a concert hall and really specifying when those paths move and where they move. Or, for example, Edgar Varèse in Poème électronique wrote a particular piece, a purely electronic piece, as a commission for this particular building, the Philips Pavilion at the Brussels World Fair in 1958. In some more kind of day-to-day examples, right, you may think about being at the theater and listening to surround sound 5.1 as an example of sonic diffusion or an acoustical engineering problem. I want to move to something a little more abstract, although I hope that you'll be able to see how this abstraction is related to something that is actually audible, and that is the actual movement of musical objects within a space. So those objects could be notes, or chords, or scales, etc. This is research that's based on a sub-branch of music theory called mathematical music theory, to name a few of the main writers in it: David Lewin, Brian Heyer, Dmitry Tomashko, Rachel Hall, Jason Eust, etc. And so hopefully this can actually be audible, and that you can kind of see the connection when we actually demonstrate some of the concepts. And in this short amount of time, I'm just going to demonstrate a very sort of fundamental concept, which is the concept of musical shape and spatiality and circularity. So on the right-hand side, you see a Western piano keyboard. It in itself has a particular shape, right? You see the white keys, you see the black keys. You also see that one of the notes, or the notes repeat after 12 notes, right? So at every 12 notes you get an octave, what we call an octave, and an octave is a note whose frequency is 2 times that of the lower octave. If you imagine that you take the keyboard and you take a line and you wrap around the C's and kind of match them together, you get a circle, right? And we call this in music theory circular pitch class space. So we're kind of moving from a linear model to a circular one. Now, when you actually tune this thing, right, to give particular frequencies to these particular notes, usually you kind of conceive of the distances between the notes as equal, right? So the distance from the C to C sharp would be the same as the distance from the D to D sharp. Right? So if you measure the ratios of the frequencies from two consecutive notes, they should always be the same. And in the modern world, we call this equal temperament. Now, what I wanted to do in this piece is to write for just intonation. And just intonation is the type of intonation that relies on scales based on small integer ratios, based on the assumption that the intervals between notes would sound better if the ratios were based on small integers. So, kind of in a physics 101 sense, you can look at the fundamental frequency of a tone, and it's, say, a sine wave, and you have the second harmonic, which is 200 hertz, right, in this example, which is triset of the first, and so forth and so on. So, kind of basic sound physics, you get kind of the superposition of these waves, and you get a more complex tone. Right? So the idea is that if I take the ratios of 5 to 4, or 4 to 3, or 3 to 2, these ratios would become the basis of these intervals. And these intervals aren't necessarily going to line up with the equal temperate intervals that we saw in the previous slide. There are precedents for this in other contemporary music. So, for example, the music of Harry Partch, Lou Harrison, and a couple of others as well, James Tenney, for example. These are some people who have worked in alternative tunings and just intonation. So, looking at the mappings of frequency ratios to the cent scale. The cent scale is this kind of 1200-point scale, which maps the total chromatic. In other words, if you go from one note to the next octave, right? So on the left-hand side, you can see that the difference is always 100, right? It's just everything is very even. On the right-hand side is the particular just intonation scale that I used. I mapped it logarithmically from the low integer frequency ratios, and you can see that those numbers aren't as rounded, right? And you can also see that there's some asymmetry there, so the distances between notes isn't always the same as it is on the left-hand side. So this is actually rather profound compositionally because it means that I have a greater option of interval sounds to choose from when I actually write my composition. It'll also be striking for most of us because most of us are used to the tuning on the left-hand side when we listen to a normal piano compared to that on the right-hand side. I'm going to play this particular device here. It's kind of an example of I think, a computer program called CSE. I can't remember, I think Aaron Hunt is the name of the composer and theorist who designed it, but you can maybe see a demonstration, I think, first of the ET scale sonically, and then the particular just intonation scale that I use. So that was the ET scale. So that was the scale that I used for my composition. And here I'm just playing around with the interval sounds. See, that one's slightly higher than the other. Okay, so when you map these tunings onto the circle, right, on the left-hand side you get basically the hours on the clock, right? Everything is equal. On the right-hand side, I've kind of mapped out to the positions they would be on the clock right? And you can see the asymmetries within each side. You can see the asymmetries. Although I think there is a symmetry from the left to the right side, and that's because the tunings are actually symmetric relative to the very middle point of these just intonation scales. So I think this is a pretty useful visualization of the type of tuning that I'm trying to incorporate into my composition here. So I'd like to end by just playing a short excerpt of the composition. I worked with Gabriela Diaz, our violinist here, who plays a lot of contemporary music in Boston, member of Sound Icon and many other groups, and also my colleague Robert Ward, a guitar player. And they have certain experience in actually playing this music, this type of microtonal tunings and these alternative tunings. And so we work together very closely to try to listen for these distinctions between something that is, say, 386 cents and something that might be bigger or smaller. So that was part of the rehearsal process for me. So what this forced me to do as a composer was to actually think about notes not only in terms of their letter names, but also in terms of their ratio numbers, right? So I would think to myself, instead of writing an A note, I have to think I'm writing 3/2, right? For those musicians out there. If I'm writing a G note, for example, I have to think I'm not writing just a G, I'm not writing any G, I'm writing 4/3. And it really forced me to kind of reevaluate my own compositional process and my sense of artistic expression. So what can this all mean? Geometric and spatial structures allow composers to recontextualize prior assumptions about music and explore new working domains. A composer can draw upon both prior musical practice and the mathematical literature to utilize alternative tuning systems in their music. And spatialization, in musical terms, can help us visualize music in ways that are both musically, artistically, and mathematically meaningful. So thanks for your attention, and look forward to continuing this conversation.
Thank you all for coming tonight again, and also thank you to Deborah for inviting me and Hubert tonight. When Deborah asked me about my work and how well it fit the topic, I said, well, it's not pinpoint, but it skirts the topic in several different ways, and I will explain what those are. My work is mixed media. I do animation and music, and the animation is often informed or driven by musical processes. So as a composer, I'm looking for ways to apply the principles from music composition into the into the visual realm. And as many great artists and certainly many composers have noted, there are quite a number of similarities between these two media. My work has evolved over the last 16, 70 years or so. I typically produce one so-called concert animation. That's a work of about 8 to 10 minutes in length per year. That includes a lot of rendering time, production time on the computer itself, and about 2/3 of the time is actual composition and creative activity. The work has evolved quite a bit. I'm always interested in new ways of generating imagery, and to say the least, I think it has evolved quite a bit from the types of things I was using in the beginning to more recent work, and that often involves hand-drawn imagery, which I find particularly gratifying. So that's one area that I'm always looking for, and I'll explain a little bit more about that in a minute. What I find most fascinating is the ability to apply musical concepts to a sequence of images, and these are just a few of the principles that any composer, any young composer even would be familiar with. And the fun part is figuring out how they apply. What exactly does transposition mean in a visual sense? What is modulation? Is that a color change? Is it a movement of some sort across the screen? Orchestration, again, what are we orchestrating? Is it visual elements? Those sorts of things are always the challenge for me. And when I do speak about this, I like to show by model some of the common terms that any theorist would know. And if you look at the terms chromatic harmony, atonality, triads, and such, you might be surprised to find that they all came from a text on art. So for me, the big challenge is finding these comparisons between the two media, and that's one of the main areas of interest for me. The other thing that I think really applies tonight is the use of generating images from scientific and engineering domains. So using things like fluid dynamics and particle systems for the imagery is an area that I'm very interested in. And similarly, there are aspects of sound synthesis that also involve modeling of some sort or another, and I'll explain both of these in a few minutes. So fluid dynamics, which you may be familiar with, really has to do with the movement of liquids and gases in particular. It could also apply to air traffic flow and a variety of other things that are essentially natural phenomena. And when you put these into a software context, you really have tremendous ability to define what those characteristics will be. I'm now taking the software that is used by engineers on a routine basis and putting it into a fine art context. And that's where I find a really fascinating potential for this. The earliest modeling was way back in the 20s. This is a very well-established field. It's all been quite well developed in software, so the tools are readily available for this sort of thing. It doesn't take the supercomputers anymore or a room full of computers. I could probably do it on my cell phone at this point, but the sound wouldn't be so good. And similarly, the tools to model musical properties, basically the properties of a musical instrument, the amount of air that goes through it, the temperature of the air, the friction of the material against the air. These are all things that I can model very easily, and I will give you some examples of these shortly. Just to start out, I'll show you what a typical example would be of the type of gaseous or liquid movement that you might find just by default. So without doing anything particularly creative or anything, with any individual personality to it, I can model fire and fluids and these things fairly easily. Adding a little bit of turbulence, the imagery can get considerably more interesting very quickly. Again, these are all almost off-the-shelf resources that the software provides. And then getting into something a little more interesting. Let's see, I can add a texture to it, something that would deform the images quite a bit more. And that starts to get a little more interesting for me. Finally, I can add an animation to the texture itself so that embedded in the gas, embedded in the fluids is a pre-existing animation of some kind or another. Could be a talking head or something along those lines. And finally, I've also used this same technique with motion capture data. This isn't me by any means, but it is something you can find easily on the net. So any sort of motion capture data, which is very, very common and really accessible, can also be applied to the same sort of fluid dynamic technique here. Similarly, there is a synthesis software for physically modeling the sound of an instrument. And this is very different from analyzing a waveform and looking at the components of it, which is a technique called additive synthesis. Here, I'm taking all of these factors of the instrument, the things that contribute to its sound, and I'm modeling them, and then I'm solving that as an equation, taking specific values for the thickness and the materials, and putting those into the sound, and I can come up with sort of realistic, natural sounding music that has that quality. So what I've found really of interest is to combine the physically modeled sound with this, fluid dynamic modeled imagery and look for ways to combine those. I'm also working with some particle systems, which is another resource that's often found in either Hollywood games and special effects, or there are some engineering applications here. And this is very similar to another musical tool called granular sound synthesis, which sounds just like it might. Many small individual fragments of sound that are contained within a cloud, where the individual note is just irrelevant. It's all about a large effect. This is something that was really uncovered by a composer named Iannis Xenakis, who was in a building at some point. He was in the Greek resistance, in fact, in the Second World War. And he heard the sound of rain coming onto the shed that had a tin roof, and he said, "Aha, that's it." And he went on to, for the next 40 years of his career to work with the concept of grains. I'll give you just a couple of examples of this, and then I'll show you an actual clip from a video that combines some of these ideas. So this is just a default emission of 1 million or so grains. Who's counting? It's kind of an off-the-shelf resource. I can make that much more interesting by adding a tail to every grain and having the tail persist, so that the movement across the screen is quite a bit more interesting. Multiple emitters with tails can produce these grains at different points on the screen, and of course the movement across the screen is completely controllable. And then I can combine these two ideas. I can use the movement of the fluids to drive the grains. This is something called particle advection. So now the grains take on more of a fluid-like motion. And then an actual example from a piece uses this idea of particle advection to model what is essentially a fluid and in kind of a turbulent way. And this time I've added the music using the granular synthesis technique. think these engineering tools have a lot of potential for integration into a fine art context, and my goal for the near future is just to explore them and look at different ways to combine them with the audio and then find a way to shape that into an integrated composition, which of course is the hardest part of the whole process, and hopefully that will continue to evolve. Thank you very much.